Welcome all the participants. Yes. Welcome all the participants for day 8 of our online FDP or Smart Variable Technology Opportunity and Challenges. So today we have expert with us, Dr. Deepak Ranjan Nayak. So he is currently working as an assistant professor at Department of Computer Science and Engineering, MNIT Jaipur. He has completed his PhD from NIT Rourkela, okay, and he has completed his postdoc from IIITM Kanchipuram. Sir is currently working as an assistant professor at CSE department, and prior to that, he has also served at SVNIT Surat with the capacity of the assistant professor in computer science and engineering department. So, sir, research interest lies in medical image analysis, machine learning, deep learning, pattern recognition, computer vision, and hyperspectral image analysis. Sir has published more than 75 articles in a reputed journal and conference. Sir has also working currently on 3 different research projects. And sir has also received a few honor as a international travel grant for paper presentation at ICIP in 2013. In 2020, he also received a 2020 CMES Young Researcher Award for outstanding research in a computer modeling and simulation. So, sir is also received the outstanding reviewer award for his research contribution in a computer and electrical engineering journal. And sir also received the best paper award for international conference and advanced computing, networking, and informatics. So, welcome Deepak Ranjan sir. Now it is over to you, sir. Please, sir.
Yeah, thank you very much, sir, for the warm introduction, and thanks for the opportunities as well. Thank you so much, sir, for the opportunity, for sharing my experience with all the participants. Yeah. So, okay, just a minute, sir. Yeah. So, am I audible properly, sir?
Yes, sir. You are audible. Please,
okay,
sir.
okay. Thank you very much once again, and good evening all. So the topic for this particular session, which I'm going to discuss, is on introduction to medical imaging and computer-aided diagnosis, right? And probably in the next session, I'll be talking about how to use the important, networks, or you can say technologies, whatever we are talking about, something called as convolutional neural network and certain deep learning algorithms. So before we get into actually how to use those technologies or those advanced algorithms to solve or to design this computer-aided diagnosis and all, so you must have idea behind the computer-aided diagnosis, what exactly it is, and what is the actual meaning of this medical imaging, and how it has, it can say, revolutionized the field of AI in healthcare. Right. So in this particular talk, I'll be touching upon several things. I'll start with asking you some questions. So, like, what do you mean by image interpretation, and why interpretation of the medical image is very difficult for us, right? And what are the different imaging modalities which we have seen, and how it helps the doctors in solving the problems, in performing the operations and all. What are CAD systems? What are traditional CAD systems? You might have been listening to many speakers since last couple of days on different on various machine learning and deep learning algorithms, right? We'll see how we can use those algorithms to design the CAD systems. And especially in this particular session, I'll be focusing on machine learning based CAD system, and we'll also talk about some of the limitations of the machine learning based CAD systems, why we're not interested in machine learning based CAD system nowadays, why people are talking about deep learning based CAD system. At the same time, we will also see some of the possible solutions. I mean, what are the limitations and possible solutions, the stages involved in computer-aided diagnosis system, especially traditional machine learning based computer-aided system, some of the challenges which also we'll see later on, that how to address the challenges that are encountered while solving the problems using or through medical imaging, right? So I'll show you a couple of pictures. Please try to interact with me. I know that you cannot unmute your mic, but you can simply write your answers in the chat box. So try to interact throughout the session, right? And if you want, if you have any questions, right? So I'll definitely discuss at the end of the sessions, right? So no worries. So let us first see some of the pictures, and then we'll try to interpret the pictures, right? And here is just a glimpse of work what we do at our vision analytics and pattern recognition labs. Mostly we focus on analyzing images and videos. So that's why I've chosen the subject as medical image analysis. Especially, you can see there are multiple works which we solve at our lab, right? And all those works are related to medical imaging only. And there are a few works also on computer visions, right? Okay, so I should not actually even discuss the importance of AI in healthcare. Probably this, the thing has already been discussed. But one of the part you can see over here is nothing but medical image diagnosis, right? So this is what actually which I want to focus. Although other parts have been also discussed by some of the other speakers, or will be discussed by some of the speakers, right? Maybe in next 2-3 days, right? So what I'll be focusing on only this part, that how these imaging modalities or how medical imaging is now helping us or helping the doctors to solve many problems, and how to and what are the problems they face while manually interpreting these images, and how to help them or how to assist them in designing some sort of automated approaches. That is what is the main focus of this particular session, right? Fine. So let us first discuss what do you mean by image interpretation, right? So when I say it is image interpretation, it is nothing but understanding each and every content of this image, right? So image is nothing but a two-dimensional matrix when it is, stored in a computer. So it can be two-dimensional, it can be even a three-dimensional, even more dimensional matrix. So mostly it is a two-dimensional matrix, consists of number of pixels, and each pixels here, right, is two informations. One is its position, basically we call it as a coordinate, and the second one is the color value or the intensity value. So every pixels in the image, right, is nothing but is having two things. One is its coordinates, that means its positions in the image, and another one is the intensity values or the color values, right? Or you can say the color values or the intensity values, right? And that is why actually we are getting colors. Okay, fine. So basically, image is nothing but a and you can say collection of pixels arranged in a two-dimensional grid or two-dimensional matrix or array, you can say, right? Where every pixel consists of two things. One is its coordinate, and the second one is like the intensity values. And these intensity values actually lies from 0 to 255, right? I'm considering an 8-bit image right now. So it will be an grayscale image. A grayscale image, so it is like the intensity values lies from 0 to 255. If the image is 8 bits, so there will be total 256 number of colors, and the values are from 0 to 255, where 0 stands for black, 255 stands for white. And if it is a color image like this particular image, so you'll be having 3 channels of the image, right? And all the channels, right? That means every pixel in this particular color image, you will be having 3 different values. For R channel, for red channel, for green channel, or for blue channel. These are some of the ideas we must have, right, before analyzing the images, right? And in this case, we are considering actually medical images. That we'll see also later on, right? So there'll be basically 3 channels: red channel, green channel, and blue channels. Every pixel in the image will be having 3 different values, and all the values will be lying from 0 to 255. And sometimes, if we want, we can also make it right, or we can normalize it and we can make it from 0 to 1, right? This is also possible, right? Sometimes we usually normalize the values from 0 to 255 to 0 to 1. Fine. I mean, different representations, right? So just now we have just talked about the 2 different types of images, and there is something called as a binary image, right? Where every pixel value, binary image is nothing but a 1-bit image, and this RGB is a 24-bit image, right? So there's 8-bit for each of the channels. In total, it is 24-bit, right? And the number of colors possible in this case is 2 to the power 24. In this case, for 1 bit, it is 2 to the power 1, which is 2, which is nothing but black and white. Only you will be having pixel values black and white. That means you will get only image having black and white pixels. That is binary image. Sometimes it is also important in case of medical imaging. I'll talk about it later on. And another one is a grayscale image. I'll show you some images that corresponds to binary. I mean, some medical images, some that corresponds to grayscale, like CT scan and magnetic resonance imaging you might have seen. There are also images like dermoscopy images, fundus imaging, and there are also other images like pathology image and all. So they belong to the color image, right? And color image actually is nothing but is a 24-bit image, and where every pixels will be having 3 different values with respect to 3 different channels. That is what actually we have discussed right now, right? And the image size, basically, if I write over here 512 cross 512, that means the image is having 512 number of rows and 512 number of columns, and the total number of pixels in this particular image is 512 into 512, right? So this many number of pixels in this image we have, and the origin always starts from here. So this is actually the 0 0 position, and the second position in this direction will be 0 1, and like this. So here it will be 1 0 like this, right? Fine. So you can take, sorry, you can take x-axis in this direction, so y-axis in this direction. You can just interpret this image is nothing but a 2-dimensional function, which is f of xy, where f is nothing but the amplitude or the intensity values, and xy are nothing but the coordinates of this particular image. Fine. So it is like 0 0 1 0 2 0 like this, and then 0 1 2 0 in these directions, right? So x-axis is vertically downwards, and this y-axis is here, right, towards the right side. That is all about the image, right? And if I ask you right now, interpret this image, that means I want to understand each and every content on this image, what you will do, right? If I ask this question to you, so definitely you will tell me that this is maybe a sunset view or probably something else, right? So this you can tell me easily because you have seen these contents several times earlier. This is what you know, right? You have seen these contents earlier. But if I show you again this picture, probably you may tell me the contents that are present in this image, but there is something very different, which is I mean, you can say it's non-natural, right? So that means something is there which is not obeying the laws of nature. If I show you this picture, ask you the same question, can you interpret this image? So interpretation is nothing but understanding each and every content of the image. So probably you may face some difficulties, right? Can you tell me what is this image, or what are the contents of this image? Can you interpret this image? I'll wait for 10-20 seconds. Wait for your answers. Yes, can you type your answers in the chat box? The question is, Sam, can you interpret this image? Can you analyze or each and every content of this image? We're slowly going towards medical imaging, right? Yeah. Okay, we should not then much wait for much more of the time here. Okay, fine. I could not see any answers in the chat box. Let me reopen the chat box. Yeah, still there are no answers. Hope I'm audible and it is visible. Okay. So the question was very simple, right? I mean, can you interpret this image, right? So that was the question. So the answer should be yes, right? Yes, we can interpret this image, but there are certain things which is something very different. What is this? Of course, you can see over here, right? So what it has been observed that this image has been, you can say, created artificially. Right? So somebody has tampered this image, and this image has been created artificial, but still your answer should be something, right? If you, in this case also, if you want to analyze the image, so probably you may analyze the image because most of the contents, all these contents, right? So this content, this content, this content, this content, this content, everything is well known to us. Only there is an issue here. There is an issue. What is that? That the model, especially the image, has been created artificially, and that is what also you need to identify, right? Whether an artificial image can be processed through a computer or not. Now, let me show you one more picture here, and this is what is the picture. Let's say this is given to you, right? And now we want to analyze this image, right? So we want to analyze this kind of image. So now can you tell me, right, what are the contents that are available in this image? The same question again. So we have seen this image. We could able to identify most of the contents. We could also able to see this image and we could able to identify all the contents because we have seen all these contents. Could see one answer, that is a satellite image, although it looks like that. Actually, it is an histopathological image, right? So it is a histopathological image, or you can say it's a medical image, right? There's a digital pathology image or histopathology image, basically used to detect certain types of cancers, right? So you can see over here. And if I ask you that based on this image, can you tell me something about this image, or where is the lesion, or where is the abnormality, right? And where is the abnormality cells, where is the normal cells? Can you tell me? I don't think so, right? Because it is difficult for us to interpret this kind of image because we have not seen this kind of images earlier. So if you have not seen this kind of images earlier, so it will be difficult for us to interpret this kind of images. And this is how one of the medical imaging modalities, right, looks like. And you see how difficult it is for us to analyze or to understand each and every content of this image because we are unaware of this kind of images. But still, we are interested in analyzing this kind of images, right, with the help of the modern days AI technologies, or you can say cutting edge deep learning technologies, right? So then what is medical imaging? And now let us try to formally define what is medical imaging and what are the medical imaging modalities we have and why it is important and what are the things, right, the doctors can see with the help of these medical imaging modalities. So this medical imaging is the process of creating digital visual representations of the interior of the body. So in early days, right, the doctors used to perform operations to know what exactly happened to a particular organ, right? But nowadays, with the advent of these medical imaging technologies, the doctors can see inside or the interior of a human body, and they can easily see what has happened to a particular organ, right? Based on some of the symptoms or based on some of the, you can say, based on the nature of the you can say the problem statement and all. So they used to recommend you should either go for this tech, either go for X-ray, either go for CT, either go for MRI, or you can go for ultrasound and all, right? So there are different imaging modalities which we have. There are some pros and cons of each of these medical imaging modalities. There are medical imaging modalities which are, you know, which gives excellent resolutions of the tissues like MRI, we know, but some, you know, there are some medical imaging modalities which are cheaper, like X-ray is a cheaper one, but MRI is really a costly one. So which one we should go for early, to detect, let's say, fractures, to detect some brain disease and all. So accordingly, doctors used to suggest or recommend us to go for this medical imaging test or this medical imaging test or like that, right? So here are some of the medical, the list of medical imaging modalities which have been extensively used in the hospitals or in the radiology centers or in the research centers to identify certain disease, or you can say to diagnose certain diseases, right? Like X-ray, CT scan, ultrasound, PET, electromicroscopic imaging, and magnetic resonance imaging, which is one of the most powerful medical imaging technologies. And then for most of these technologies, if you go through the literature, you will find many of the inventors, those who have developed like magnetic resonance imaging and all, they have been awarded Nobel Prize, right? Because it is really very, very important, right, for the society, even for the doctors as well. So that doctors can see inside a patient, right, or inside, or they can see the interior of a human body without cutting the human. It's not about that that's not the only one benefit which we have, right? So doctors can also see the important things which is also not visible to the human eye, right? Like the molecular structures and all, which is not visible to the doctors even after opening, right? Or you can say the whole body and all, they cannot even see. There are some things which is not visible to the human eye, right? Like the molecular structures and all, which can also be, right, visible through these medical imaging technologies, right? So this is one of the most important point, right, which I'd like to highlight here. It enables the doctors, the radiologists, to see inside a patient without having to cut them open, right? This is very, very important thing. So let me show you some pictures, right, which I've taken from a research paper uh, recently. That here is just a glimpse of different types of medical imaging modalities, or you can say medical imaging or medical images, right? Medical imaging is the process, and the medical images are nothing but the output of those particular process, right? Which you got obviously in the form of digital images, and that is why we're interested in processing this kind of images with the help of digital computers. Fine. So you can see there are some, there are some MRI images, there are some CT scan, there are some CT scan images, there are some X-ray images, right? There are some dermoscopy images, again some MRI images, there are some colonoscopy, endoscopy images, there are some histopathological images, there are ultrasound images. There are different types of images you can see, and it is difficult for us. Uh, it is difficult for us to actually analyze this kind of images, right? Because these are not natural images. Like I've shown you two pictures, right? In the previous slide, which are natural images, and we know each and every content of this image, but unfortunately we do not have much idea about this kind of images, right? So that's why we always need the help of the doctors to, right, to label this kind of data, right? And so that we can design some sort of algorithms, right? I mean, there'll be some inputs in the form of these images, these medical images, and there must be some output, right? I'm talking about only supervised setting, right, where we'll be having X, we'll be having Y, and where you want to just the relationship between, or you want to draw the relationship between X and Y. So X in this case is nothing but this images, and this Y is nothing but the level, right, which must be provided by the doctors, right? And then only you can make relationship between X and Y. But getting these levels are very, very difficult, right? Because we all know how difficult it is to get the medical images and even to annotate these medical images, right? So we'll see later on what are the issues we always encountered while analyzing this kind of images, and what are also CAD systems and all. Right. I hope at least you have got some idea behind medical images, how it looks like, and how it is different from the natural images. So and we have just now seen, right, how it is different from the natural images. And here is just an example, okay, of different types of medical images. Just now we have seen. Okay. Okay. Now there is a question, of course, that comes to your mind, right? Definitely, that is what is, if this task, right? So this task is currently done by the radiologist, of course, or by the doctors, right? They are also interpreting all these images, and of course, finally giving us a report, and of course, giving us finally, suggesting something, or let's say they are also providing recommendations and all. So now the thing, then what we want to do here? What is our task, and what are the limitations of manually interpreting this kind of images? So there are images, like let's say, for example, I'm considering there is a colonoscopy image here, right? So this is a colonoscopy image, and this basically this colonoscopy images are very, very important to detect something called as polyps over here. You can see. So these are actually small growths that are formed in the inner walls of the you can say the colon, right? Or let's say what is your task, right? Of course, the task of the doctors here is to identify all these polyps, and these polyps are like the growth, or you can say a bunch of cells, right? And if it is not detected properly, so this may lead to colorectal cancers, right? So this is what is known as CRC, and colorectal cancers is the third most common type of cancers across the globe. So in here in colorectal cancer, the miss rate by the doctors is in between 6 to 27%, which is a really high number, right? So that means if one of the polyps is missed here, and that may lead to colorectal cancer. And missing polyp is a common thing by the doctors, right? Because the miss rate is always in between 6 to 27%. It is only because of the challenging properties of these polyps. The polyps are having camouflage properties. The textures, the color of the polyps is sometimes very, very similar to its surrounding tissues. So that is why sometimes it is very, very difficult to identify the polyps, even by the experts, right? And one of the, if one polyp is missed, then that polyp may lead to colorectal cancer. And initially, the patients are unaware about the polyp developments and all, right? So then how to identify those polyps, right? Precisely, and how to provide the boundary of the polyp so that the doctors can resect or the doctors can remove those polyps accurately, right? And sometimes it is missed by the manual process. So the manual process is always observer dependent and it is subjective in nature, right? So that's what we know, right? And it is of course time consuming, and there are also several other benefits, right? It varies from person to person. That is what is known as inter-observer variability, right? And there is also sometimes, right, we may find that something called as intra-observer variability. If you go to the same doctor multiple times, maybe the same doctor give you different opinions, right? So that also happens. So mostly inter-observer variability is the most common thing which we observe, and we usually solve this kind of problem with the help of majority rule. We used to go to three doctors, then we used to apply the majority rule, that out of three doctors, two doctors are saying the same thing. So then let us also go ahead with that majority rule, and basically whatever you want to do, right? So there are multiple things actually which we face while manually interpreting this kind of images. Even if the experts, right, they may face also difficulties. They cannot sit for 24 hours, they cannot analyze the images all the time and all, right? So that is why we're interested in designing some sort of computer-based algorithms which can also detect this kind of polyps, which can also tell, yes, there is a polyp here, which can easily classify or assign a label, or let's say let's say labeling is like providing grade to a particular tumor, right? Let's say your task is a brain tumor detection problem, or it's a brain tumor grading problem, where your task is to take an image as an input and just grade the tumor, whether it is grade 1, grade 2, grade 3, grade 4, and whether the tumor is there or not. Like that is a kind of classification problem where your task is to just assign a particular level, right, with respect to each of the image which is given to us. It means again, X in this case is an image, the Y is nothing but a grade, or Y is nothing but a level that will be assigned to this particular image, right? But in this case, it is something very different. Here, your task is to also highlight the boundaries, or you can see the whole region where polyp is residing, right? So that means this particular task is known as something called as segmentation. We'll discuss in detail, right? Because we'll be having one dedicated session on segmentation algorithms, and that is how actually, right? Segmentation is very, very important for the doctors to identify the accurate boundaries, and those boundaries are very important for removing the polyps or for resecting the polyps, right? We'll discuss in detail. So two different kinds of problems. Just now we discussed, one is like classification and one is segmentation. We'll also see what is the difference between classification and segmentation, and whether we can design a similar type of algorithms that is being used for classification, whether we can also use the same type of algorithms to solve segmentation problem or not. There are a couple of things, right? So sometimes your input is an image, the output is nothing but a label. Sometimes your input is an image, output is also an image. In this case, especially, you see the input is an image, so X is an image, Y is also an image. But sometimes X is an image, Y is simply a label, right? It could be anything. We'll discuss in detail later on. These are actually some of the problems, right, of, you can say, manual interpretation of these medical images. It is time consuming, very expensive, error prone, of course, right? And it always requires skilled supervision because it is observer dependent, right? So that is why we're interested in automated, process, or you can say automated diagnosis of those kind of disease with the help of course, cutting edge AI technologies and computer vision algorithms, especially. So when people thought of developing this automated process to ultimately help the doctors, it's not like we need to keep the doctors and all their decisions. So of course we need to, our main goal here is to assist the doctors so that the doctors can take better decisions, and this kind of systems or this kind of model, whatever we're planning to design, they can just use it as their secondary or can supplementary tool, right? And then they can verify their decision, whatever they are making. Fine. So that is what is the major goal here. So let us talk about something called as, computer-aided diagnosis. Sometimes people used to also call as computer-aided detection. Right? right? So sometimes people are calling it as CAD, sometimes people are calling it as a CAD, which is computer-aided detection, and other multiple, you can say terms people are using to define the same thing, right? So where your goal is to actually design a computer-based algorithms to diagnose certain disease. Let us also talk about the history of CAD system, right? So as soon as it was possible to load the medical image into a computer, right? Because the outputs of the medical images are in the form of course, digital images. So that's why people have shown their interest to analyze the images with the help of a digital computer. But you know that, yes, in early days, there were no such deep learning algorithms and machine learning algorithms, right? I'm just talking about, 1960s and 70s and all. So at that time, so people have developed CAD systems with the help of traditional image processing algorithms. And the tasks were like low-level tasks. Is given a medical image, how to enhance the quality of the image, how to enhance the contrast of the image, how to enhance, or you can say how to remove the noise from these CT scan images, which is a very common problem, right? And how to identify the edges of the tumor, or you can say the boundaries of the tumors and all. So these are certain tasks for which people have developed CAD system in early days. But later, in 1990s, the serious and systematic investigation on CAD system started when this neural network, support vector machine, and all those algorithms came into the pictures. But we all know that these algorithms are data driven, right? And it needs a lot of data. That means input and output pairs, because these are all supervised techniques, which we know. So that means we need to have multiple medical images at the same time, the levels, and then we can design these, machine learning based techniques, right? Or you can say machine learning based CAD systems. So we'll see in detail. So what are the process involved in machine learning based CAD systems, right? And now with the advent of these deep learning algorithms, even we are interested in designing the CAD systems with the help of these deep learning algorithms, which you have also studied in this particular program, right? You might have heard about something called as convolutional neural network and all, right? I hope it has been already covered. Convolutional neural network and some sort of generative, deep learning models and all. Also, we will see that how we can use this convolutional neural network based, how we can use this convolutional neural network to design the CAD system, and what are the benefits of that, and what are the weaknesses of traditional machine learning based CAD system. Fine. Yeah, just now we talked about the importance of the CAD systems, right? It helps the radiologist in accurate interpretation of the images using dedicated computer systems, of course. So when I say dedicated computer systems, it involves all those things. It involves image processing algorithms, right? It sometimes also involves computer vision algorithms and machine learning or deep learning algorithms as well, right? So to provide second opinions. So there are multiple advantages, which is listed over here. It improves the diagnostic accuracy. It lightens the burden of increasing workload of the doctors. It also reduces, right? It also reduces intra and inter-reader variability, which is just now we have discussed, right? Right. And here is some of the tasks, medical image analysis tasks for which CAD system have been developed over the years. Classification is the most studied, you can say, right, task for which CAD system have been developed over the years. So when I say classification, it is nothing but given a set of medical images, your assign is to just assign a level. Well, it could be also disease grading, like tumor grading problem, which we discussed. And it could be object detection and lesion detection. It is, let's say, an brain MRI image given to us, and then your task is to only locate, right, where the tumor is. You need to only locate where the tumor is. You need to basically provide a bounding box, right, where exactly the tumor is. And there is something called a segmentation, which we will discuss. We have a separate session on this. We'll discuss in detail how this detection and segmentations are different, and what are different types of segmentation approaches we have, like semantic segmentation, instance-based segmentation, and panoptic segmentation. We'll discuss in detail in that particular session. And we have something called as alignment problems. It is very, very important, right? Sometimes it is known as registration, is the word actually, medical image registration, where your task is to align the images, right? Basically, a certain image. If you want, you can also go through the literature on these different types of tasks for which CAD system have been developed. And there is something called as a context-based image retrieval, right? Where given basically in one image, right? You can also identify the similar type of image that is present in your database. It has a lot of applications, right? And the most important, as I said, that is the most extensively used or CAD systems, right? Or the most extensively designed CAD systems is only for the classification and segmentation. You will also find a lot of CAD systems on object detection, lesion detection, registration, CVIR. There are also problems like synthesis, right? You will also find synthesis problem, right? Where your task is to generate, or you can say generate some synthetic medical images, right? Which is also the current trend in the field of medical imaging, right? So how to use these generative models like GAN, diffusion models and all to synthesize the medical images, especially the training images, and to use those images to train, because we do not have much amount of data in this case, and most of the deep learning models demand huge amount of data. We will discuss in detail later on, right? Let us see what are the stages that are involved in a machine learning based CAD system. Let's say I want to design a CAD system for tumor classification problem, tumor classification task or tumor grading task. And for simplicity, let's say I am choosing there are only two classes, right? So every image, whatever is given to me, these are all brain MR images. Brain MR images are given to me, and I want to assign a level either normal or pathology or abnormal. Normal means the image doesn't contain any abnormal regions. That means the patient is not having any brain disease. Abnormal, the patient is having some type of brain disease. The brain disease again is of different types, right? If you want, you can also extend this problem to multi-class, where you can also assign a particular a label, right, with respect to this abnormal category, right? So again, in that case, the classification task is going to be a multi-class classification task. But for simplicity, I'm taking two classes. One is normal and one is abnormal. This is what is your task. So how to solve this problem with the help of traditional machine learning based system or traditional machine learning, right? So this is what is given to me is nothing but set of MR images. That means this is like X for me. A set of images, you can say the training images is given to me, and also the corresponding label is given to me. This is like XI and these are YI, and where I varies from, let's say I varies from 1 to n, capital N, and capital N is nothing but the total number of images I'm having, or you can say total number of training images I'm having, right? So this is X and this is Y. So what I just want to build a relationship between X and Y, and I want to design the model. I want to design the whole CAD system over here, so that in future, if I pass any brain MR image to my CAD system should predict either it should be normal or abnormal. That is what is the task over here. I hope the task is clear to everyone. Fine. So what are the steps? Let us see that a typical machine learning based computer-aided diagnosis system includes. The very first is you will find is always is nothing but known as image pre-processing, right? Image. So these are all pre-processing parts. These are also pre-processing parts. These both of these stages are nothing but the pre-processing part. So when I say image pre-processing, what does it mean here is that means I am checking here, is there any image available in the data set which is darker and which is contaminated by noise. I don't want this kind of inputs. I want the inputs or the images should be free from noise, and the images should not be darker. It should have good contrast. So that means the ultimate goal of this stage is nothing but to enhance the quality of the image, because my task is to assign a label with respect to each of the input image. That means I want to analyze the patterns. Those labels can be assigned by looking at the unique patterns that are present in this image. And those patterns, those unique patterns, are nothing but known as representative or features of those images. But if the image is contaminated by noise, the image is a darker one, if it is a low contrast image, so probably you won't be able to identify those unique and crucial patterns from these images. So what we want here is, we want to first remove the noise if it is present, and we want to enhance the quality of the image so that the patterns can be easily, you can say, extracted from the images. So that is what is the major goal of this pre-processing here, just to enhance the quality of the image, right? Either by removing the noise or by enhancing the contrast of the image, right? So there are multiple ways to do this. Fine. There is one more stage here, which is known as ROI segmentation, that is region of interest segmentation. Sometimes, right, we don't want to extract the patterns from all over the image. We want to only extract the image, let's say, from this part, right? Because this is the part which basically influences the output. That means we can say this is the part where most of the abnormality is present. I don't want to look at other areas where there are some black pixels. You can see this is a whole image. You can see there are some redundant features. These are not important for us. I want to only focus on this. I want to only look at these features. So what I can do is I can simply apply some algorithm over here. First segment, to identify or split this split the image into different regions, and I want to only highlight this region, which is very difficult again, right? Because this segmentation itself is an independent task for which you can design the CAD system. But here we are using this ROI segmentation, right? Is nothing but a stage which is coming under the pre-processing stage. That means where you want to only focus on the important regions and you want to ignore other regions. That means you want to only look at the patterns of this region, not the other regions. And again, it is a difficult task, as I'm saying. Again, this problem can be solved using supervised algorithms, also using unsupervised algorithms, right? But unsupervised algorithms are not sometimes that accurate. So probably again, you need supervised algorithms. But again, supervised algorithm means for segmentation, you need X as well as Y, right? So ROI segmentation is possible if the segmentation map, or you can say the mask, is given to us, and if you are designing, if you're trying to, if you're trying to design something called as a which algos. Okay, I'll discuss at the end, right? Which algos of the supervised. Okay, I'll discuss. That those are like learning based, right? When I say segmentation, supervised, these are all learning based segmentation algorithms, right? Learning based segmentation algorithms, example, convolutional neural network. For example,
Deepak sir, you are not audible, sir. Deepak sir, are you there? Deepak sir? Participants, am I audible? Not sure. It seems that sir connection has lost. Am I audible? Okay, okay, okay. Mute कर लो थोड़ा. Participant, sir is joining actually because of some internet issue, sir just got disconnected. So, sir is joining in 2 minutes. Please be here. Okay. Sorry for interruption.
Yeah, is my screen visible?
Yes, yes, sir. Yes, sir. Your screen is visible.
Yeah, I connected from my mobile phone only. There are some internet issues from my side in my department. I don't know. Maybe because of rain and all. Okay, no problem. Uh, Screen. Yeah. So what I was discussing actually is nothing but the whole, you can say the typical machine learning based computer diagnosis system, where we have talked about something called as a pre-processing stage, right? The goal of pre-processing is to enhance the quality of the image. And where we have seen there are two steps, like removing the noise, enhancing the contrast of the image. At the same time, this kind of ROI segmentation is not mandatory, right? It is an optional stage. If you want, you can do this, right? If you find the abnormalities, or you can say the important patterns that are present all over the image, it is difficult to again do these ROI segmentations, right? So these are like optional steps, right? Or sometimes required. You need to check whether you need to identify the ROI first and then identify the patterns or not. So then the very important stage in any machine learning based system is nothing but known as feature engineering. So when I say feature engineering, of course, the goal here is to identify the features or extract the features from the pre-processed images or from the images, right? So when I say features, so the features could be anything. There could be different types of features which you can extract from the images. The features could be a shape-based feature, or geometrical based features, or geometrical shape based features. It could be color based features. It could be texture based features. It could be anything, right? So there are different types of features which you can extract from an image, right? But the problem here is that how would you decide that whether shape feature is going to help us, or color feature is going to help us, or texture feature is going to help us, or there are several others, as I mentioned, features we have which can be extracted from the same image. How would you decide that which feature you should extract? Unless until you are a domain expert in the field of feature engineering, it is very difficult for us to define that which of the features are going to play a very important role here. And there are also certain other limitations of this kind of feature extraction process, which is known as static. I'll discuss later on this one. Let's try to remember that the kind of features which we extracted using this particular system, or using any of the feature extraction algorithms known as feature extractors, these features are known as static, and this whole process is known as static feature engineering. Why the features are static? Because the kind of features whatever we have extracted is not going to change by looking at the errors or by looking at the output. You are not looking at the output, you are simply extracting the shape-based features or the texture-based features from the images, and ultimately store the features in the form of a feature vector. So the features are always stored in the form of a feature vector. We'll also discuss, right, what kind of features we can extract from these images, and can we directly consider these pixels as the features or not, right? Can we directly consider these features as the features, or I mean these pixels, right? Sorry, the raw pixels of the image as individual features to represent a feature vector. As I mentioned, that always we extract the features, whatever the features may be. It could be shape-based features, color-based features, texture-based features. You need to ultimately store the features in a feature vector, and these feature vectors can be processed easily through the classification algorithms or classification techniques, which are of again different types, like nearest neighbor, Bayesian classifier, support vector machine, random forest, decision tree, maybe neural network, and so many classifiers will be having, right? But we were discussing something called as feature engineering, where the goal is to extract the features, store it in a feature vector, and there is an optional stage over here, which is known as feature selection, or feature reduction, where your goal is to select the important features and ignore, or you can say remove the unimportant or redundant features from this feature vector, right? So this D sometimes even could be greater than 100, could be greater than 1,000, it even could be greater than 10,000, right? Sometimes. So we don't know how many features we should extract or how many features are sufficient to represent this particular image, right? So we should take all the pixels. This D value is going to be very, very large. We don't want to have such a large dimensional feature vector, because again, if your input to the classification algorithm is going to be very, very large, the complexity of the algorithm is going to be very large. At the same time, there are some algorithms like neural network and all, and because of this high input dimension, the number of parameters are going to be very, very high, right? We'll see what will happen if the number of parameters in the neural network is going to be very, very high, and why we're interested in extracting the features rather than using the raw features, right? So that is what actually is our goal here, is to extract the features, store it in a feature vector, and this D value should be again dependent on the kind of features you are extracting. And sometimes, right, sometimes what we find that yes, not all the features are important for us. So at that time, what you can do is you can select the important features from this set of features, whatever you have extracted. Let's say you have extracted D number of features. D is nothing but the dimension of the feature vector, and you want to identify that whether all D features are important or not, right? So it is like features. I'm talking about feature selection. Feature selection is a kind of subset selection problem, where the total number of possibilities in this case, or subsets, is nothing but 2 to the power D minus 1, where 2 to the power D is the number of subsets possible using D number of elements in a set, and minus 1, that means I'm not considering the phi set. You need to at least take one feature, right? So phi is like, always there's a phi in the total number of subsets in that set, particularly power set and all, what you know from your college of mathematics. So I'm not considering phi over here. So that means if you are having n number of features in a feature set or in a feature vector, you need to, first you need to identify 1023 number of feature sets, and you need to tell out of these sets which set is the most important one. So using trial and error process, you have to first, you can say, run your model for 1023 times, which is not practically feasible. If even the value is greater than 10, so it is going to be very, very high, right? So we have algorithms like, filter based algorithms, wrapper based algorithms for feature selection, based on which you can select the features. There are also other approaches like feature dimensionality reductions, where you can reduce the dimension of the feature vector from D to D dash, and where D dash is less than D, right? And that is also possible by the linear combinations of these features. There are algorithms like PCA, principal component analysis. There are algorithms like linear discriminant analysis can be applied over here to reduce the dimension of the feature vector. In that case, the original features will not be retained, but you can simply reduce the dimensionality of the feature vector, right? Let's say this is the part of, again, the feature engineering, where you have applied, some approaches to extract the features from the images, and then you have the feature vectors. We are applying some sort of feature selection algorithms or feature dimensional reduction techniques to have the important features with the feature vectors, and to remove the other unimportant, or you can say the redundant features from the feature vector, right? And then once you'll be having an optimal set of features, right? What you can do is you can just pass, or you can process those features with the help of classification algorithms. And those classification algorithms could be k nearest neighbor, and which we discussed just now. And finally, now let's say finally what you have done is you have built the model. You have built the model and you have designed the classifier. When I say I'm designing the classifier, means you have, you can say, optimize the parameters of the classification algorithms. If you are dealing with neural network, let's say, for example, neural network contains a lot of parameters, which are nothing but W and D, weights and biases you might have heard about. And these weights and biases are nothing but the two parameters, not exactly two parameters. This weight could be in the form of the matrix. So there could be millions of the numbers, thousands of the numbers that this W matrix can contain, even the B vector can contains, right? And what you have done just now is you have extracted the features, right? And those are static features. And then you have only trained the classification algorithm to, right, to have the optimized value of W and B. You have not trained anything else here. You are only training the classification model, right? And now your training part is done. And next time, what you will do is that during testing, you will pass a test sample, which is XT, let's say, for example. You will again apply the same sort of rules, whatever you have done, the same features you will extract, and you will send it to the trained classifier. The classifier has already been trained. That means the W and B value has already been adjusted, or you can say trained or optimized. Now you are going to use those adjusted values, right, after extracting the feature during the testing, and then you will get obviously a level, right? Either normal or abnormal, right? So then you can check that whether the classification is correct or classification is wrong. And these are the stages actually which we always consider while designing machine learning based CAD systems. But let us now discuss about some of the limitations of this. Yes, of course, there are limitations. All these, it involves lot of stages. All stages are dependent to each other. If you are not pre-processing the images correctly, you cannot able to extract the important features. If you are not extracting the important features, then you cannot even classify those images appropriately. At the same time, there are a lot of algorithm literature for feature extraction. Decide that whether I should take shape-based feature, color-based feature, texture-based features, geometrical shape-based features, or there could be different types of features we can consider. How do you decide that the best feature extractor algorithm? At the same time, how do you decide the classification algorithm, right? And again, the combinations of the feature extraction and the classifications, right? It always creates a problem while designing the machine learning based CAD system, that how to choose an appropriate feature extraction algorithm in classification algorithm, as well as the combinations, what is the best combination of the feature extraction algorithm as well as the classification algorithm we have, right? So that is what is we are interested in here, how to overcome these kind of problems which we face in case of traditional machine learning based CAD system. As the major concern just now we have seen that the two most important stages is of course feature extraction and classification. And just now we have seen for feature extraction we have different types of features, right? These are some of the algorithms: wavelet, edge detection based algorithms, histogram of gradient, local binary pattern, shift invariant. So the shift is also it is also very scale invariant, right? Feature transform. So these are very important. You can say feature extraction algorithms that has been applied in several fields of image processing and medical imaging as well. But you need to have some domain expertise to decide that what kind of algorithm is going to be useful for us. Now, can you tell me how many classifiers have you heard about? How many classifiers? The name of the classifiers. Can you tell me how many classifiers you have seen in machine learning? Maybe the number. Can you tell me? You can write it in the chat box. How many classifiers? Yeah, classifiers I'm talking about. Yes. How many classifiers or how many algorithms, right, you have seen in machine learning or you have implemented or you have, or maybe in some books? I mean, I'm just asking how many. I mean, here are also you can see, right? You can see 1, 2, 3, 4, 5. So how many classifiers? I mean, may I know the number? I mean, 10, 15, 20 or like that. How many classifiers you have implemented or you have seen in machine learning? Yeah, it could be binary, it could be anything. So it could be binary, even it could be anything. Okay, 7 to 9, right? Okay, it's interesting. So I mean, if I ask you the same, how would you decide? I'll give you in a problem statement of, let's say, tumor classification where there are different MR images given to us. I mean, basically magnetic resonance image given to us, and your task is to classify the images into certain categories. Let's say your task is to decide or use a single classifier out of all classifiers which you have studied. So which classifier you would decide, I mean, which classifier you will select to solve your problem, and on what basis you will select your classifier. Of course, there's no such theorem, right, available till date, right? So that how to choose the best classifier, and is there any classifier which will work well data sets and all. Till date that this algorithm is going to be useful on all types of data sets and like that. But there are also a couple of studies in the literature which you can go through, and you can see that what are the algorithms, based classifiers, which have been very successful on a diverse set of data sets. I am having something to very important concept to show you. Let me show you this particular slide. In this particular slide, I want to highlight something that is there is a paper in the literature you will find that was published in a very top-tier journal known as JMLR, that is Journal of Machine Learning Research. And the title of the paper is, "Do we need hundreds of classifiers to solve real-world classification problems?" This is what I can say is the title of the article or the paper that was published in 2014. And this is a 50-page paper. And the paper is also cited a lot of times, right? The paper has been cited a lot of times. I mean, many people have followed this paper. Fine. So in this paper, they have not developed any machine learning classifiers. Rather, they have analyzed, or you can say they have evaluated the effectiveness of 179 classifiers. You have told me 9 classifiers exist, right? And even it is difficult to identify a single classifiers. But there are 179 classifiers exist in 2014 in the literature. And what they did, they have evaluated the performance of 179 classifiers over 121 datasets collected from the UCI repository, right? And all these datasets are different. They are having different number of samples, different number of classes, different number of features as well, right? And after applying these many classifiers over these many data sets, you know how much difficult it is, right? It's really difficult even to implement one particular classifier on 121. So after applying this after actually applying or evaluating, right, 179 classifiers over 121 diverse set of data sets, they come up with some suggestions for the reviewers, or for the readers, right, like us, that a random forest support vector machine with some of the kernels, like nonlinear support vector machine, and there is something called the extreme learning machine. I don't know how many of you have heard about ELM, right? ELM is actually a kind of randomized neural network, right? This randomized neural network, and why the name is so-called extreme learning machine, it is not only the one kind of randomized neural network. There is also another kind of randomized neural network which is very, very popular, known as RVFL, right? Random vector functional link neural network, very, very popular neural network, right? So these are actually known as randomized neural network, and this extreme learning machine is a kind of algorithm. And this means in this kind of architecture, so you'll be having only one hidden layer, and that hidden layer, right, I mean, it will be like one input layer, there will be one hidden layer, and there will be one output layer, right? And input to the hidden weights will be random, and these outputs will be computed using some sort of analytical approach. That means you are not going to apply here any gradient descent approach, any derivative based approach to identify or to optimize the weights and the biases. So you are not going to use any gradient descent algorithm here, right? So it is independent of gradient descent algorithms, and that is why, because gradient descent is the iterative approach, so it is actually, right, gradient free learning approach. So that means it is not at all iterative based approach, and that is why the learning is faster, and the name is so called extreme learning machine, right? You can just go through the paper and all, but including these three, so you must have also something called as neural networks over here, feed forward neural network, right? So that means what they are claiming, that these algorithms are really performing well on a diverse set of data sets. So you may choose these data sets initially, right, to solve your problem. And if it is not working, so you may go for other classifiers. That is what is the recommendation, right, from the authors of these papers. And that is why you might have seen in some of the research papers, what people are doing is they are computing their basically their classification task with the help of several classifiers, and then they finally come up with some suggestions or recommendations. Out of all these classifiers, this classifier is going to help us for solving our problem. Whether it is feature extraction, whether it is classification, we'll be having many classifiers, many feature extraction algorithms. But the problem lies here in selecting the best classifier and the best feature extraction algorithm. And of course, the combinations of the feature extraction and the classification algorithm. That is the major limitations of the machine learning based classification, or is machine learning based CAD system. And the limitations, let us discuss, right? Is another limitation here is the kind of features, right, which you have extracted is static in nature. You can see over here, the kind of which you have extracted is static in nature. So when I say static, that means you cannot modify these features. You cannot modify these features by looking at something. And which is also because the kind of features which we have extracted, I don't know that whether these kind of features are going to be helpful for me or not. I don't know whether the features which I've extracted are going to be helpful for me or not. So you don't have options here to readjust the features or to go back to the feature extraction algorithm, update the features, right, according to the output which we have. You have the options to go back to the classification algorithm and readjust the value of W and P. That is what you have done. That means you have applied learning, right, on the classification stage, but there is no learning in the feature extraction stage. And that is why these features are static in nature, right? And that is what we do not want. There is no learning. You can see over here. I've just taken an example of a natural image over here, but you can see over here, this is an input image which is given to us, right? And there could be different types of feature extraction algorithms I may have. I can apply edge algorithms here, right? Edge detection algorithms to detect the edges, which will be helpful for me to have some shape-based features or boundary-based features, whatever. There could be also raw pixels. I can also use raw pixels as a feature extraction algorithm, but which is not always a correct way to extract the features. We'll also see later on. There could be some dedicated feature extraction algorithms that can be used to extract the features, like Sieved, HOG, or probably some other types of features like texture features and all, which can be applied to get the features. But again, what I mentioned here is, yes, of course, the kind of features which we're extracting is a fixed feature, is a static feature, right? It's an handcrafted features. We are applying some algorithm and we are getting this. We don't have any options here to modify these features. And what we're trying to do here is in the classification stage, you can see we have weights. These are all weights, and there are biases also over here, let's say. And we are using some neural networks. And what we're trying to do here is we're learning the weights and the biases of the neural network. We're not making any learning in this feature extraction stage. And that is where also we are missing something. That means the features are static. We're not updating the features by looking at the output and all. And that is why these machine learning based CAD systems are not very popular, because the features are static, and choosing a best classifier and a classifier as well as the feature extraction technique is very, very difficult. And that is why we are very much interested in deep learning based algorithms, and we'll see how these deep learning based algorithms are trying to overcome this problem. You might have also seen maybe tomorrow, and I mean, I don't know whether yesterday or day before yesterday you have seen the concept of, or you have studied the concept of deep learning and all, but that is again going to be useful in this case. Yes, I'm not interested in discussing, right, these features and all. So let me just show you one example, right? What are features, and why one type of features are sometimes not sufficient to solve the problem. For simplicity, I have not taken here medical images. I have taken some natural images. I mean, animal images especially. Here are the two different types of animals I have chosen, and right, one is horse and one is zebra, and I want to extract the features from these images. So now my question is, can I use shape as a feature? This is a shape. These are different. You can say the two shapes, right, of the respective animals which we have seen here. And now if I ask you which one is horse and which one is zebra, can you tell me? Right? It is difficult, right? Because sometimes shape itself is not sufficient, right, to tell us what kind of object it is, right? So similarly, you can also relate this with the medical imaging domain. The shape itself sometimes doesn't give the information about the different types of tumors. So here, what is very important in this case is texture, right? You can see the body color as well as the body texture, which varies. So we can, extract the texture features rather than taking shape-based features. Or what you can do, you can take the shape-based features along with the texture features, right? You can take the combination of the features to solve the problems. That is what is my actually intention here, to keep these photos and all, so that you can understand that sometimes one types of features are not sufficient. We have to include more number of features of different types to solve the problem, right? These are like texture-based features. I don't want to discuss much about it, right? Fine. So these are some of the points which we discussed right now. That what are the limitations of the machine learning-based models, and of course, the solution is what is the solution then? What is the solution? So instead of using static features, if I use a dynamic feature, if I can learn the features instead of extracting the features manually from the images, if I can learn the features along with learning the weights and biases or the parameters of the classifiers, probably my problem is going to be solved. And that is what actually the deep learning people, right, did, that they used to develop something. They have developed something called as deep neural networks. And one of the most popular deep neural networks used for solving image and video centric problem is known as convolutional neural network. You might have seen in convolutional neural network, there are convolution operations, very, very important, right? And those convolution operations can be static. Maybe in case of traditional machine learning based CAD system, you can also apply convolution operations, but like to perform edge detection or to extract some of the edges from the images. But we don't want to fix the filters. We don't want to fix the filter coefficients. We want, right, the values to be learned by the model, right? Because we do not know what kind of features is going to be useful for us, right? So that is what actually we want to do, and that is where we are interested in learning both the both the feature extraction stage as well as the parameters of the, what I can say, the parameters of the classifiers. So now the thing is, what do you want to learn in the feature extraction stage? What we know that yes, there are, you might have seen in image processing, those who are having image processing background, they might know there are convolution operations and how to apply edge detection or how to apply edge detection filters and perform the convolution to get the edges in the image. So, I mean, you can either consider some, edge, vertical edge-based filters or horizontal edge-based filters. Like you might have heard about something called as the Sobel filters, Kenny filters, pre-Hewitt filters, right? So those are like 3x3 filters, let's say decided -1, -2, -1, 0, 0, 0, 1 to 1, like for vertical edges, right? And these are the filter weights, or you can say the kernel weights, which can be involved with the pixels of the whole image over here to get this kind of output. I don't want to just put these values as a fixed value here. I want to learn these values, right? Along with learning the weights and the bias values of the classifiers. So how to do this? Yes, it is possible. We can also learn this kind of meaningful kernels. It's not about only one kernel. You can also, if you want, you can learn multiple number of kernels to extract or to learn multiple informations from the same image, right? That is also possible. And it is dynamic I'm talking about, right? Because I want to learn these weights with the help of, again, the same base propagation algorithms, which is usually used in neural network. So that means what I'm trying to do here is, instead of using handcrafted kernels like the Sobel filters or kernels which I've just now seen, right? Can we learn multiple such meaningful kernels? Yes, we can do it. And if you want, you can also repeat it for certain number of layers to extract the information different levels. You can say the abstract level from the you can say fine grained levels to the abstract levels, right? It's like that only. I will discuss later on. Fine. So that means, can we have multiple layers, right? Where every layer will be having many number of such kernels to extract different information. You can see over here. So initially, you may have some layers, which will help us in extracting the generic features, and maybe in the later layers, you will be having some specific features, right? Very, very specialized to the input image which you are having. And this basically, right, motivates to develop something what is known as convolutional neural network, right, which we have seen earlier. Motivates us to design something called as a convolutional neural network, where your task is not to use the feature extraction algorithm, not to use the fixed kernel, rather to learn the kernels along with learning the classifier. That means we want to make the system end-to-end learnable, where you will pass one input at the one end and you'll get the output at the other end, and all the stages, you'll get the error at the output. Here you will get the error, or you can say the loss, and this loss will be propagated to all the layers because all the layers are here trainable. You see, that means you have modify the features. Let's say you have extracted the features by means of some filters. Let's say those features are not important, cannot be some important, cannot be useful for us. So that means because of that particular features, you are getting some loss over here. And now you can just reduce the loss just by going back to that particular layer, modify the features, modify the kernel coefficients, subsequently modify the features. Again, you check the loss, right? If the loss is really reduced, then you can again go back and try to further reduce the loss by modifying this, right? This is what is the the forward and the backward process in backpropagation algorithm. That is what in traditional neural network, right? And that is why we are very much interested in convolutional neural network, right? Not the traditional machine learning based algorithms where every stage and identifying or selecting classifier is always a concern, right? And there are, of course, certain properties of these deep learning based algorithms. Just now we have talked about it, enables end-to-end learning, which is a very powerful property of deep learning algorithms. And it doesn't require any manual feature engineering, which also we have seen. It can be easily retrained for other recognition tasks. We will discuss later on. What do you mean by this? Let's say we have designed something. We will see that how to, retrain, or how to reuse, or you can say how to reuse or transfer the knowledge of, the architecture, whatever is already been designed to solve a similar type of task. We'll see later on, but yes, there are a lot of advantages of deep learning algorithms over machine learning algorithms. Again, there are also some limitations, right? It always demands huge amount of data, but in medical imaging, it is very difficult to have huge amount of data, or to design a large data set. And because annotation is really a costly process in case of medical imaging. That is what we discussed earlier. Although the collection of the image has become easier, but the annotation has become very, very difficult, even because of the unavailability of the doctors, right? And the annotations for some cases is extremely difficult, like segmentation and all. The most successful type of algorithms we have is nothing but known as convolutional neural network and vision transformers to analyze the images and videos, right? And convolutional neural network we have already studied, right? We'll see how to use this convolutional neural in the next session, how to use this convolutional neural network, right, to solve medical image analysis task. And here are also a couple of things which I will discuss in the next session, and then we will discuss what do you mean by transfer learning followed by attention mechanisms and all. Okay, thank you. I'll stop here, and if you're having any queries, you can write in the chat box. I'll be happy to take it. I'll again start the next session after 5 minutes, right? If you're having any queries, you can just write it in the chat box.
मिनट कब बैक नहीं वो यहाँ पे नहीं दिख रहा है.
So if you're having any queries, right, that is related to the first session, you can write it in the chat box.